We are glad to present our work, GGPT, Geometry Grounded Point Transformer. 3D reconstruction is a fundamental problem. Serving as the classical foundation for 3D reconstruction, structure from motion methods produce geometrically constrained results. However, it lacks general scene prior and heavily relies on dense input captures. Recently, feed-forward regression emerges as a new paradigm. It has simple architecture and is highly efficient. Thanks to data-driven prior, it can produce reasonable geometry, even for sparse input views. However, due to lack of geometry constraints, their results often misalign with the ground truth and are 3D inconsistent, and they fail to generalize to out-of-domain scenes. For example, depth anything 3 reconstructed points can deviate from the ground truth and have large error. The artifacts are more pronounced in scenes different from training data, such as human body. Given the pros and cons of the two types of methods, we are motivated to use the constrained geometry estimated by SFM to enhance feed-forward reconstruction. We propose geometry, Grounded Point Transformer or GGPT, which can use reliable geometric guidance to augment various feed-forward reconstruction. The improvement can generalize across out-of-domain scenes. Given a set of input images, a feed-forward transformer, such as VGGT, predicts point maps and cameras, yielding a dense yet geometrically inaccurate point cloud. To refine this dense cloud, we propose 2 stages. First, an improved SFM to estimate geometry guidance. Second, a conditional 3D point transformer to combine the guidance and the initial dense cloud into a refined cloud. Specifically, in Stage 1, we develop a new SFM pipeline, which is faster and more robust for sparse input views. First, we use the camera endpoints predicted by VGGT as an initialization. Second, we use dense matchers, such as Roma V2, to extract multi-view dense matchings. From them, we choose a small subset of tracks for a global bundle adjustment. Next, we use the optimized cameras by the BA and the whole set of valid tracks to triangulate points with an efficient direct linear triangulation. Compared with previous SFMs, we utilize dense matchings rather than sparse key point matchings. This provides richer geometry cues and enhances the robustness to low overlap cases. To reduce the computational costs of using dense matchings, we run separate BA and DLT on sparse and dense matchings, respectively. Experiments show that our SFM outperforms previous SFMs in both efficiency and accuracy. The Stage 1 gives us a geometrically constrained point cloud. However, it is incomplete in textureless and monocular regions, so the next problem is how to utilize the partial guidance to refine the initial dense points. Our solution is to train a 3D point transformer that conditions on both the regressed dense cloud and the partial cloud and predicts the final refined cloud. For both input clouds, we encode their points with positional encoding, learnable type embedding, as well as the point correspondences. We feed the point features into a point transformer V3 architecture. Note that in the point transformer, we apply point attention based on spatial proximity instead of 2D grid attention, which distinguishes our method from prior 2D-based geo-conditioned networks, such as POW3R and MapAnything. Experiments show that with the same training data, using a 3D point transformer can achieve better generalization than 2D transformers. Altogether, when evaluating point accuracy, GGPT improves various feed-forward reconstructions across multiple datasets. The metric gain is pronounced in out-of-domain test sets, including human body and surgical scenes, which share significantly different geometry and appearance than the training data. Visual comparison shows that our method can effectively reduce the error and mitigate 3D inconsistency. Regarding inference speed, GGPT sacrifices real-time inference for higher accuracy. We acknowledge this as a limitation. However, it is still substantially faster than prior SFM methods and offers an agreeable trade-off between accuracy and efficiency. Another limitation lies in its inability to extrapolate the geometry guidance to distant monocular regions, which we aim to improve in our future work. Thanks for your watching.